of your assignments, you had this question. It's to figure out how is the power set of the natural numbers related to the size of the real numbers. Are they the same, or one is bigger? And the thing that I'm skipping, it's in my notes, algebraic numbers. Just very little information. I think you can just read it in my notes. Not a big deal. What we talk about today is metric spaces. So, the idea of a metric space is that you have some environment in which you have some notion, just a very primitive notion of space, not actually vector space necessarily, but a notion, a collection of points, and a distance between those points. So, you would have M, some collection of points, and a notion of distance between these points. And you will write it as M comma D. To D we'll speak about it shortly. That will indicate what we mean by distance. Okay, so then let's see what do we mean by this distance. Let's see what properties should we have. So distance, it's always a property that takes in 2 points and produces, it seems, a positive or 0 number. So we should think that the distance should be a function from M cross M. In other words, we need to take 1 point and another point from M to the closed interval 0 to infinity. And that I mean the distance could be 0, the distance could be some other number, but it is definitely not infinite distance, and it's definitely not negative. So what properties should a distance function satisfy? Well, the very first property is the distance from one point to itself should be 0. So distance from x to x should be 0 for all x in M. So you remember the symbol, that means just any x you pick. The distance from a point to itself should be 0. Now, another interesting quantity that we think the distance should have is if I take x and y, how should that be related to the distance from y to x?
The same.
The same, right? In other words, it should, if I take the same route one way and I take the same route the other way, the distance I measure should be the same. We'll see examples of maybe where that might be violated, right? Examples of things that look like a distance, but that is violated, so that's a strange situation. Now, that's the 2 properties, and what other properties do we want the distance to have? Maybe one more that is less obvious. Triangle inequality. And the third, usually the hardest to verify, is that the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. And it's called triangle inequality because in our ordinary space, if this is x, this is y, if I take a detour to the point z, it seems that from Euclidean geometry, this is distance x to z, this is distance z to y. The sum of those distances should be longer or equal to the distance of x to y. Okay? I mean, clearly it could be equal if I take z to be a point on my shortest round. Okay? That's so that it reminds us of what we mean in the distance back home. So, what examples of distances are there? So there is a very natural example. If you take m to equal to r, you have and you take distance between x to y to equal the absolute value of y minus x. This you know as the standard distance, the standard. Maybe you can say Euclidean distance on R. Okay?
Is that us thinking on the one-dimensional plane?
Yes,
like
that's
on the number line?
when we have this distance. So R, you can think of it as a number line. It's a one-dimensional linear space. And you're acquainted with this absolute value function. That's how we ordinarily measure distances. Naively. That's the Euclidean in R. So, we can say that another example is given, first of all, given any m, we can define the discrete distance. By the distance from x to y, it's equal to, there are two possibilities. Either it's equal to the number 1, and that's if x is not equal to y, or it's equal to 0 if x is equal, if y is equal to x. Okay? So this will define, this is one example of a distance on any metric space. It has its uses, although it seems almost a bit trivial and a bit scary. So if you imagine your environment, and this were the distance. So the distance from here to that room is 1. So is the distance from here to Paris. I could just in one motion, I jump, boom, I'm in Paris. I jump, I'm out of this room. Okay? And then if you try to think about such a space, what sort of possibilities are there for velocity, right? Is velocity necessarily constant or not? Actually, a lot of basic ideas that you might have about locomotion might be a bit weird in such a metric.
Yeah, that's great.
So another example that we must notice is that, so those are the very, very basic examples. We can say that if A is a subset of M, right? And we have basically, that's how you write it when you need to specify the distance. So if I have MD, that means I have a metric on the set M. I have a notion of distance, in other words, some function that I fix that satisfies those conditions. In other words, you see, it is equal to 0. I should also say, maybe I should add in this first property that distance from x to y equals 0 if and only if x equals to y. That's an important thing that I should add, right? So the distance between two distinct points should never be 0. So if A is a subset of M and M has been given a distance, so it's a metric space, and then I can then simply say that AD is a metric space. Because, well, I already specified how to measure the distances over all of them. This is just measuring the same distances, but on a restricted subset of M. Okay? So aside from that, we have several ways of generating new metrics from old ones. So I call it internal method. For creating new metrics from old. So the idea is going to be the following. So suppose that I have, given a given metric space MD. Suppose we have a function f that takes m into n, or it takes m into n, and this function is bijective. Okay, it is bijective. So then I can define a metric on n, call it n rho, and I can define the metric on rho by just looking at where the points came from, right? So I can say by rho of x, y will be the distance of f inverse x, f inverse y. Here, and that's for all x, y in n. Okay, that's one way. Just in other words, if I have an injective map, I can then use that map to define metrics. Another version of this idea, and I'll give you examples so you'll see how it works. Another version of the idea is, suppose that I have a function rho f. Well, let's call it, maybe use f here. Let's call it g from m into r. And all I'm requiring is that this function is going to be, so this g is going to be injective. G is 1 to 1. So what I can then define is, I can define a metric on M by stating that the distance from x to y in M will be simply the absolute value of f of x minus f of y. Okay? You see what I do? I borrow the distance on R, I inject M into R. In other words, what is the idea here? I take that space, I unravel it, here is a picture. So you might have, the idea is, here is your set M. It's like twisted coil, right? And the function f, the function g, sorry, is just taking this m and stretching it along the real axis. So that image of the straight line that I drew here is g of m. So that allows me to measure the distance between any 2 points, x, y. Where have they gone? They have gone here. So the points might have been here is x and here is y. Okay? So in essence, you can think of it either as taking m and rectifying it. It's like a rope when you stretch it along r. Or you can imagine that this curve has been assigned numbers. Okay, so let's see how that is supposed to work with basic examples. So let's consider simply functions so let's consider reassigning new metrics to R, right? We really haven't not developed any interesting spaces to deal with, and most of the ones that we will deal with relate to R in one way or another. So let's suppose that we have the function from g from R to R, and what the function is doing, so let's say g of x is simply x divided by root of 1 plus x squared. Okay? This function you can check is 1 to 1, not onto. Okay? Yes?
Yes, over here you have dxy equals absolute value of f of x minus f of y.
Yes, I'm sorry, I tend to write f
Yeah.
by default, and I meant g.
Okay.
Thank you for noticing. Right? So this is 1 to 1. What's going to be in fact the image? In fact, the image of R will simply be exactly the interval the interval minus 1 to 1. It will be the interval from minus 1 to 1. So this function g is just taking R and it's squishing it to the interval. Okay? And I can then define the following distance. So I can define R with distance d by, so that's a different distance d, by d xy. So the distance between x, y is not, I'm not actually going to measure, just let's say if I take x and y, I'm not actually going to measure those 2 points. What I'm going to do is I'm going to write absolute value of g of x minus g of y, which is the absolute value of x divided by root 1 plus x squared minus y divided by root 1 minus y squared. Okay? Let's consider other examples. So you see, the only thing I needed is that the map is injective, right? So what I do is I take whatever space and I somehow reassign it. Like here, I reassign it along the number line. So another example, let's suppose that I have g from R to the interval minus pi over 2 to pi over 2, and gx is tangent inverse. Okay? So this map is again, in this case, 1 to 1 and onto, but what's important is that this function is 1 to 1. And what is going to be then the distance? So we have R distance 2. Distance 2 here is given by x to y equal to absolute value of tangent inverse x minus tangent inverse y. Okay? Yes?
Is this just an example of how you can define distance, or is this a popular...
It's an example of how I can create the functions that simulate my understanding of distance, right? Those functions that I define right away satisfy all those conditions, because the absolute value satisfies those conditions, and all I really do is I just relabel the points.
Is this a popular way to define distance?
There are going to be a lot of ways of defining distance. The most important way to define a distance is involving integrals, so geodesics and whatnot, and they involve more ideas, in fact, right? So I'll show you one example of a distance that is going to be weird, but so I went over that very fast. Do you follow why this automatically defines the distance, guys? Do you understand why?
Yes,
You understand what I really do? What's the one-to-one property is doing? Essentially what I do is, this is the idea. I take whatever space M, and the way I measure the distance between them is just by thinking of this as just a contorted real number line. That's what this in essence is doing, is just saying this is the same as R. That's why it works, okay? It has to be an injective map. If I kind of glue points together, it's not going to define distance, because a bunch of points, there were different points, now it's 1 point, and now the distance between them is 0. You understand? So in essence, I'm not really doing anything new. I'm really just using the absolute, I'm recycling the absolute value. Okay? When I do, you see, in this case, you would think, why do I care? This is just R. There are examples where you would care. I'm just really teaching you one idea of how you can just quickly generate many distances that relate to itself. Right here, there is no immediate reason why should I really change my space. It's already a straight line. Why do I change it? Okay, so those examples in a way are not terribly important.
It has to be one-to-one because if you map, for example, 2 points to 1 point, right, to the number 2, then 2 minus 2 is 0, but they started out at 2 different points, so it doesn't satisfy if and only if x equals y. Distance of x, y equals 0 if and only if.
So again, you see, the fact that I'm doing it with R might seem redundant. It's more important, let's say, if you're using it, let's say you have a curve, rectifiable curve, it's just twisting around in maybe 3-dimensional space or 4-dimensional space, and what you do is you just understand that it's just a twisted real number line, and this thing is just telling you how to understand it as a number line. Okay, so in a way it's trivial to do this with R. It might be less trivial when what you want to do is you want to know the position of a particle along a curve, and this is just the idea. Okay, so another example. Well, let's now just take another interval. So let's say now G is gonna take the interval 0 to infinity, and it's gonna map it to R. And what is it gonna do? Let's say what it's doing, it's squaring the number. So G of x will just be x squared. Notice it's from 0 to infinity. So this is my M. This guy is M. So then I can define metric M d3, or just M rho, by, I can say that rho from x to y is going to be absolute value of x squared minus y squared. And that defines a distance. Okay? So another example may be something like this. So we can take the interval 0 to infinity into R, and we can define the function g to take x, and it's going to be logarithm of x plus 1, for example. Okay? So this is an injective map. And what does it tell us? It tells us that I can define a function sigma, a distance sigma, from 0 infinity cross 0 infinity to R, and it's given by sigma xy to be equal to absolute value ln x plus 1 minus ln y plus 1. So this, you can simplify. I'm just trying to make it look weird, right? So this is absolute value of ln of x plus 1 divided by y plus 1. In fact, since the function is ln is always positive here, right? You see ln input is bigger than 1. In fact, I could drop the absolute value. Well, actually, you have to be careful. I don't want to drop the absolute value. I'll keep it because sometimes this point is small. Okay? So we'll keep it like this. Okay? So that's another example. All of it is just what I do is I take one space and I just stretch it or compress it, and I measure it against R.
Professor, just a quick question.
Yes.
Is it from 0 to infinity R or the other way around?
This means this is a distance function. So it takes a point in here and a point in here. Right? Yes?
I mean in the other example.
In the previous example?
Yeah.
Here.
Yes.
So the function that I defined is square. Notice that the square function is 1 to 1 on the positive interval. So that's why this thing I automatically know is a metric. Okay? I'm not saying it's necessarily an interesting metric, but I'm saying it is automatically a metric because what I just did is I related to the absolute value. We're going to learn other things, okay? Did I answer your question?
Yeah, kind of. It's just I'm thinking like G is taking us from R to 0 to infinity.
Depending on, first of all, this is what I define as the inputs, right? So sure, you see, when you think of a function, here's one thing where you have to be careful. You have to always specify not only the operation, but also the set, the domain, and the codomain. Otherwise, you haven't specified a function. Okay, so you're used from calculus to think that the domain of G is any number it can take. But if I allow G to take negative numbers, it's not going to be 1 to 1. Okay. So that's a good point. We'll return to it. Okay. So you always have to specify what is the domain and what's the codomain. Otherwise, you really haven't explained to me what the function is. And just a few more of those, again, basic examples, I hope, guys. I'm not completely causing your heads to spin. Am I? Am I?
No, of course not.
Of course not, right? So you understand what I'm talking about, right? I'm not just talking to myself. Right? I got too used to it, so maybe I just think, am I just too used to it? Do you understand me?
Yes.
What's the domain of the brain?
What's the domain of the brain?
Yeah, and where are we mapping it?
So another example is giving you just a very cheap method of creating metrics from old ones. Okay? Very cheap method of creating metrics from old ones. So here is another example. I can take G to be the interval 0 included 0 to infinity, and into R. This one is actually a little bit useful sometimes, right? So you might have G of x equal to the square root of x. And then, of course, I can define a metric. I can define a metric D from 0 infinity cross 0 infinity into 0 infinity by d of x to y, just absolute value of root x minus root y. Okay, all of those again are very similar metrics to the absolute value.
So these examples are all clear from the standpoint of it's clear that they are metric spaces.
It is clear that they are metric spaces. You can prove rigorously if you want to go over all the definitions, but the reason you can right away say they have to be metrics is because all you did when you that's why I call it again maybe. What I did is I rectify a curve in essence, right? What I do is I take some segment of space and I stretch it, bend it, whatever I do, I place it against the real axis. Okay? And what this means now what I do is I inject the numbers from the real axis onto this curve, and that's how I do the measurement. So really, I'm really measuring R. You see it? So again, the idea is simply if you take this curve, it has to be, so there must be a one-to-one map. So the one-to-one map is just really assigning numbers on the curve. So this number, let's say, is 0, this is 1, somewhere here is 2, 3, right? That's another way of viewing it. So then measuring distances between whatever points is the same as measuring the numbers corresponding to those points. Yes?
Another question would be, when we cross two spaces, when we cross 0
Right.
infinity cross 0 infinity, we're creating an xy, and that makes sense. Then our function maps an xy to a z, right? To another thing.
If you again, you cannot always draw it. Here, this is a real space or something that you can visualize. Here is something you can visualize, and this is something you can visualize, so you can draw it. Usually, it might be also a space that you cannot necessarily visualize. Okay, so this will not be R, it will be some foreign object. Okay? Okay, so you got the idea, right? You can create this as long as you take a function that takes this curve in a one-to-one fashion, right? So the way it works is curve, rectify, and rectify, that's the operation G, okay? And that's why it has to be one-to-one. It cannot take 2 points and glue them, otherwise the distance between 2 points that are distinct is 0. And measure it against rectify, and then measure against R. So this is M, this is G of M, and this is R. So you see what G of M did is just straighten this line. I mean, it didn't have to be the full real line, it just must have been some segment of the real number line. Straighten it up, and now we measure against R. It could be much weirder if the function doesn't have to be continuous. I can actually break it apart, chop it up, and place it. As long as the function is one-to-one, it will work as a metric space.
I guess a better question would be, if we're working in a two-dimensional space like 0 infinity cross 0 infinity,
Right.
how can we define a function of one variable?
Well, it's going to be a function of, again, this x does not mean one number. This x will be whatever point. It just talks about a point inside of my set. And we will see examples, so don't worry. We will see examples of Rn in general. We will define distances on higher dimensional spaces.
That's a different x, right? It's an x that represents an xy, basically.
Right.
Okay.
Right. So I gave you enough examples of this trivial way of generating metrics, and let's consider maybe a little bit metrics that are a little bit stranger, perhaps. I'll keep the definition for now. Some of them are much harder to verify that they are metrics. So this example is one of my favorite metrics.
Is it the name of it?
Metrics. And again, right, the reason it's, I would have, let me see, so when I think of this metric, it just my heart gets warm. It's so very romantic, right? You have anybody here, I mean, I'm not sure what music you listen to, do you know Anna German, the singer Anna German? Does anybody know? There is one song, very beautiful. I would have played it to you, but I'm not sure what sort of faces you will make. And if your faces will be indifferent, it will break my heart. Right? It will truly break my heart. And one of the lines in the spot, that's when I think it's, and I will hear you 1,000 miles across. We are an echo, an eternal echo of one another. Right? So the distances grow far and wide between us, but yet we hear ourselves 1,000 miles across. What sort of metric will that be? How is that possible? Well, yeah. So there is one example. It's a little difficult. So just if you just for a moment imagine that this Anna German metric so what you have is, this is just a segment of a plane, all right? And on this plane you have, this. So on this plane you have this is the y-axis, this is the x-axis, but altogether it's much easier to represent it by complex numbers. You would say that z is equal to x plus iy. After all, complex numbers, if you read a section about it, are just two-dimensional numbers, right? So if you take the plane, so this is, you can think of it as the complex plane, which is the same as R2. So then on this space, you can imagine that the two people that love each other so much that they are moving, they are hurled very far from one another. One goes this way, the other one goes that way. Okay? So the distance between them, it looks to you like it grows, but not if you take it to be the Riemann sphere. So instead what you can imagine is, you can imagine that entire space wrapped around on a silver mirror sphere. And in that sphere, here is that sphere. That's just its intersection. So if you look at it from the side, it looks like this. Okay? And what happens is that what you do is, this point is in three-dimensional space, and the way you measure distances is, you can think of the position of one person as being given, so the person is here. So this is z, and its position on the sphere is z star. Okay? The position of the other person that on the plane it looks so far away is w, where w is another complex number, and somewhere here is w star. I will send you the song maybe, if you want to hear it, you hear it. but just imagine you cringe to this. Makes me very upset. So what is the way that we actually measure the distance? It's actually the internal, again, that's my language, I'm not sure, I don't remember why I started calling it the internal method, I guess because I modified the metric inside of the absolute value, right? The way I measure the distances between them is in 3D space. I inject two-dimensional space into a three-dimensional space. And this point is associated with the coordinate 0, 0, 1, which is the point at infinity, okay? So the way I do it is the distance here between Z and W is really the three-dimensional distance, right? Between which is we'll learn it later. It's the norm of the point Z star minus W star in three-dimensional space. In other words, I take those 2 points that are floating in R3. And when you translate everything together, right, the way this works is that this distance, it's called chordal distance, it's going to be twice the Euclidean distance from Z to W divided by root 1 minus absolute value of Z squared, root 1 minus absolute value of W squared. And there are a lot of ideas that go into it. I won't explain to you why this is a distance. Really, it's immediate that this is a distance once you know how to do the projection, once you know which function is going to project onto the sphere, and once you know how to measure distances on the sphere. Okay? So in other words, yes?
Why don't we just use the 3 Pythagorean theorems to figure out, like in three-dimensional space, to find the distance between one thing to another, right? We could just keep using the Pythagorean theorem twice through, 3 times through.
Well, you have to be, so first of all, I'm not sure to which theorem, how you particularly want to do it. Really, it is the Pythagorean theorem that we measure in R3. That's what
exactly,
you
yeah.
The distance that we measure between the blue and red point is just 2 distances in R3. Yeah. Right? And I know how to measure distance in R3 for maybe Calc 3. So we are going to go over how to do that. But then what you need to know is how do you inject those maps, and then this is just the internal method. This is just applying. It looks weird, but it's really applying your obvious distance in three-dimensional space. So it's an example, an important example of what I just showed you. Okay, so this was trivial. This is an important version of what I just showed you. Okay, so in here the idea was that I take C. You see, so what does it? The Z star, right? What is Z star? So you have some function G from C to the sphere. The sphere is usually called S sub 2. Okay, indicating that it's dimension 2. It's a sphere in 3 dimensions, right? And what it does, some formula G of Z is equal to G of Z star, where Z has 2 coordinates because it's in the plane, and Z star will have 3 coordinates. And then this bar we'll learn later. Norm is just how we measure the distance in between 3 points, right? So, and we have maybe this thing. This will be root of something squared plus something squared plus something squared. Maybe that's what you refer to as the Pythagorean theorem, right? So that the indication of 2 is that you use 2 and 1/2. Okay? That's how this is going to be done.
Does the sphere have a limited number of values in it? Or does it stretch?
The sphere is basically this function is G will identify every point in C with a unique point on the sphere. The only point not identified is the point at infinity. Point at infinity, no one corresponds. Right? So you see, as they move far away in the sense of R2, they're actually getting close together on the sphere. Okay? And this is a very important metric. So if you study complex analysis, this is the metric you use. Okay? The ones I showed you are just a trivial versions of this idea. In this case, it's important. Good? with me. I did explain this. This is just you know, to whet your appetite. That's all. So here is one thing that I want to make a remark about. Be careful. So how do you be careful? So for example, suppose I have this function. So I take g from, so let's say this is g1. It's from 0 infinity to r, and g1 of x is x squared. Okay, it is x squared. Then you can say that I can say that 0 infinity d1 defines a metric space. And the metric space is what? This is absolute, so d1 of xy will be the absolute value of x squared minus y squared. Okay? We saw this example. Make sense? Now let's look at what happens if I take G2. And G2 is, again, you see, I'm giving it a different label because now I'm going to define it from R to R, right? And I'm going to say that G2 of x still has the same formula as x squared. That's your question then. See? So what happens? What happens now is that D2 xy equal to absolute value x squared plus y squared. Is it a metric space or not? Is it a metric or not? The function, is it a metric or not? Is metric or not? Look at it. Before I had the interval 0 to infinity, now I just say the interval is just all of r. Does this define a metric?
It's not onto.
And this should be a minus.
It's not onto. I mean 1-to-1.
Yes, and why is it not a metric? So this is not a metric function. When you say metric, is that thing that you use to measure distances. Okay? Not. Now why is it not? Let's just see what you see. I still have it on the board. It's very easy to verify. Let's see what happens. If I take distance from the point -1 to 1, right? Those are distinct points on R. Yet the distance is absolute value -1 squared minus 1 squared, so that gives me 0. So this fails. Why does it fail? It's because, think about what this function is doing. It takes real numbers, it folds in the middle. So if you think about this geometrically, it takes all of the real numbers. Here is 0, and then it folds. Right? It folds this segment onto itself, so it glues the two segments together. Okay? So what happens is that points that used to be different in different places in space are now glued to the same place. And therefore, it does not define a metric on this interval. Okay? The function has to be 1-to-1. So let's consider, once we had the internal method, let's consider another method of generating new metrics. I'm going to erase this. generating matrix. So again, the reason I call the previous one internal is I modify inside of the absolute value. And this one I'm going to modify outside of absolute value. Okay? That's the only reason I call it internal. External, it's not at all any language used anywhere except here. Okay? So external method of generating matrix, so we might have this. So suppose we have a function who's, with the following properties. So the function is going to be, first, the function is going to be from the closed interval 0 to infinity into the closed interval 0 to infinity. Well, that tells you what? That tells you that the function is never negative and it does not take negative numbers. Okay? I'm going to draw a picture of it so you can just summarize the picture in a moment. But that's first property. Second property is that the first derivative, again, you see I'm being a little bit informal here naturally, because we haven't really developed rigorous machinery for derivatives, but I'm just showing you, like, ahead of it, right? So once you know those the ideas of continuity and differentiation later on, then this is rigorous. So the derivative is positive for all x bigger than 0. The third condition is that f of 0 is 0. Fourth condition is f prime is a decreasing function. So it's a decreasing function, and that is to say that f prime of x plus y is going to be smaller than f prime of x. Again, x and y are positive numbers. Okay? It's decreasing. So that you can quickly see what the function should look like, it looks like a curve that starts at 0, kind of like the root function. One example that satisfies it. Okay? This goes like this. So when you think of the function that I'm talking about, right, I'm using this function. So when I have functions of that form, my claim is the following.
It's always a metric space.
Claim is that if MD is a metric space, then so is the metric M rho, where rho xy, or maybe I'm afraid to use xy too much, so rho AB is equal to the function f applied to the distance a to b. Okay, so you see, before I updated inside of D, here I update outside of D. Again, that's why I call it external. Okay, and that's for all A, B in M. Now let's prove it. Let's so prove. Actually, so first we observe that the function f at satisfies the inequality f of x plus f of y. Okay? Observe that this is going to be true. Now why is it going to be true? Well, you can just simply consider the function h of x to be equal to f of x plus f of y minus f of xy. So this is h sub y if you really want to indicate, right? Y is being fixed here. Okay? So what can I say about this function? So what I know about this function is that h of 0 is equal to f of 0 plus f of y minus f of 0 plus y. F of 0 according to condition 3 is 0. Again, just look at this picture, okay? F of 0 is 0. And therefore what we have is that this is just simply f of y minus f of y, that's 0. So I notice that the function h at 0 is 0. And now I'm going to look at the derivative, okay? So then what is h prime of x? H prime of x is going to be f prime x plus, this is constant, so this is plus 0. Okay? Derivative fy is constant with respect to x, so it's plus 0, minus f prime of x plus y. Okay? And now what do I see about it? Now I notice that h prime of x is, look at this, by property 4, yes?
No, quick question.
Sure.
H sub y?
Yes, you can erase it if you want to. This means that y is held as constant. So I do it for any y. I do the calculation this way. I fixed y and I'm going to change the x and see what happens. Okay? And then I'm going to see what happens through all the y. So h prime of x is this quantity, which is bigger than 0 by property 4. You see? F prime x is bigger than f prime of x plus y. You see that this happens if the curve, if it's concave down. You see the derivative here is always positive. That's the condition 2. Look at it, derivative always positive. But the derivative is becoming less and less positive. That's what I indicate by first derivative being decreasing. Right? The derivative is becoming less and less positive, and that allows me to conclude that h prime of x is always bigger than 0. Okay? So that, what does it mean? It means that 0, which is equal to h prime of 0, is equal to h of 0. 0 is h of 0, and that is less than h of x, which is f of x plus f of y minus f of xy, and just move it across. So the implication is what we have over here. So that implies what I wrote on the top. You see, this quantity is bigger than 0. So that means that f of x plus f of y is bigger than or equal here. See, that's the number, right? This thing is bigger than this thing. Make sense?
So what we're doing is we're creating a distance in a metric space,
right,
and then we're mapping it to another distance function, another function that defines distance in a different way that satisfies those properties, those original properties. So the first three that you wrote, the first three make sure that it's onto f of 0 to infinity to 0 infinity, whatever. All of those make sure that it's onto.
It is not. I do not know that it's onto. It does not have to be onto.
I mean, not onto. Sorry, 1-to-1. The first three properties make sure that it's 1-to-1. And
So the first properties make sure it's 1-to-1, and property 4 make sure that
it's
we
never
have.
negative.
No, it's actually going to be the triangle inequality. That's going to be a problem here. Okay. So the first properties ensure the function is 1-to-1, and that it's going to map properly. We're going to see it. Okay. So this is just a calculation, and this calculation is necessary to verify that it generates metrics. Okay. So, right, do you remember those properties? I'm going to erase this part.
So you're saying the fourth defines that it's the triangle inequality. Okay.
Yeah, so now that we know this, now let's observe the rho. Now let's see that this rho is indeed a metric. So, well, how do we do this? Well, let's calculate. First of all, I need to see that what is rho. So first part is that rho of x to x, or let's say a b. So rho of a to a. What do we get? Rho a to a is just going to be f of the distance from a to a. But we know this distance function is satisfies, it's already a distance function inside, so it's 0. So what we get is f of 0, and that has to be 0. Yes? Again, you can look at this picture to help you. Those are just descriptions that make sure that you have this picture. So that's one property. The distance between one point and itself is always 0. That's what I need. Second property that I need is, well, maybe even call it steel property. Now suppose that I find that distance from A to B is 0. Okay? Distance from A to B is 0. Suppose this is true. I want to verify that A and B are the same, right? The only 2 points whose distance between them is 0 have to be the point itself. So rho of from A to B is 0. That implies f of the distance from A to B equal to 0. Now look at the graph. The image of whatever number this is maps to 0. There is only one number. Okay? So the implication is that distance from A to B had to be the number 0. Yes? Do you see it, guys? The distance from A to B. Now I went to this function, I know it's a distance. And what does this imply? That implies that A is equal to B, because that's a distance. So we verified one property. Second property, I'm not sure if I do them in any order, I don't remember the order, but second property, let's say that it's clearly that rho AB is equal to rho BA. So, right, that's clear because rho is just a function, and if the input inside is just going to, or the distance that we have inside is already going to make sure that this happens. Yes? Guys, everybody is clear why this is true? I see strange eyes. So, okay, so why? Again, look at it. This means rho of f, this means f of the distance AB. What is that? That's f of the distance BA. So, of course, right? Because the inside operation is a distance function. So, so f is always receiving the same input. So property 2 is clear. What's property 3? Property 3 is, I would also say clearly, and I'm sorry that I'm a bit all over the place. I don't remember which way I ordered it, but clearly the distance is never infinite. Distance is never infinite. So rho of AB is, so 0 is the lowest we can get. And we are always less than infinity. Why? Because this function is defined on R. We just simply see that the function is positive, the function f is positive, and it's processing numbers that are going to be positive or 0. Right? So this is clear. So distance between any 2 points is bigger than or equal to 0 and less than infinity. Fourth property is triangle inequality. That's where you need this picture. That's always the hardest, or usually the hardest to check. Triangle inequality. Why is triangle inequality true? So look at it. So if I take rho from A to B, that is the same thing as f distance A to B. Okay? Now the function is increasing. So what I'm going to do now, I'm going to use triangle inequality inside. Right? So what is this? So this is less than or equal to f of the distance from A to C plus the distance from B to C, or C to B, doesn't matter, right? From C to B. Now, why do I know this inequality? It's because the function is increasing. You see, that's why I needed it to be increasing. Right? So, what you see what you have by the triangle inequality of the input, right? This is smaller than this. You see, this is smaller than this by triangle inequality. Now, if you feed f a bigger number, you get bigger output. Yes? And then the last part is this. F of a sum of two numbers is less than f of one number plus f of the other number. Which is the rho of AC plus rho of CB. And that is for all, or for any A, B, C belonging to M. And this proof is then complete. You see, I verified triangle inequality. It works as a distance function. So let me give you very quickly. How much time do I have? 2 minutes? All right. So maybe one example. So look at this, right? So I can take R together with absolute value, right? And let me define f from 0 to infinity to 0 infinity by f of x equal to root of x. So that means that the implication is that if I take R and I define the distance rho, where rho of xy is just going to be root of absolute value x minus y, is a metric. You see, I used root, right? The reason for that is that the root function, so this is root x, right? The root, sorry, I'll just write it root without the, right? This is the root function. So by the external method, you see this updates my metric and it's not going to change it. Okay? Right, so we'll make sure you know this well. I'll see you next Wednesday, or this Wednesday. See you Wednesday. Bye.
Next Monday we don't have class. I'm not sure. So we're gonna receive our homework and then we're gonna turn it in.
But basically, if you can do the homework for Wednesday in a week and a half,
Yeah.
assignment 2, and we'll see from there.
Okay.